Final practice, extensive characterization of materials. Okay, so the objectives of this practice is to demonstrate the acquired knowledge during the whole semester in the laboratory of materials behavior. This practice involves the 7 practices done during the semester. The materials and equipment. The material given is the steel 1045. The equipment was the universal machine, optical microscope, hardness machine, machines for metallographic preparations, and machine for impact tests. Okay, so the experimental procedure for the practice is divided in 4 tests. The metallographic analysis, which includes the calculation of grains size at micrograph at 500 times. And it needs to have a good quality and visible grain separation. For the tensile test, you need to obtain the graph after doing the test, analyze the results, and do some proposed improvements to the one done in teams. The hardness tests are the Brinell, the Rockwell, and the Vickers, and you have to analyze each one of them. The impact test you should be done at room temperature. Now, the order is tensile test, hardness test, metallographic test, analysis, and impact test. I'll explain in a while why is this done this way. First, the tensile test. The deliverables are broken specimen, analyzed and interpreted graph, values for tensile strength, maximum strain, yield strength, elastic limit, elastic modulus, percent of elongation, and percent of area reduction. The machine used was the universal machine, such as the one seen here. Here's where the specimen goes. Okay, so the results, as you can see in the pictures, it was a ductile fracture. The material was 1045. The calibration length was the 75.98 millimeters, 2.99 inches. The initial cross area was 172.7 square millimeters and 3.92699 square inches. The head advance speed of the machine is 25 millimeters per minute. The loading point 2 of the formation was 0.75. The last load was 22K, and the final length was 88.9 millimeters and 3.5 inches. And the final cross area was 126.6449 millimeters squared, or 0.1963 square inches. This is the graph done. This line over here represents the elastic deformation. This is the way the material behaved, this curve. This point right here represents the point where the yield strength is at its maximum. And if you return the material if you release the material from the machine, it's supposed to return to this shape. After this point, it's the plastic deformation, and it gets until this point, which is the ultimate strength, where it breaks. Here are some of the data obtained. The ultimate strength in foot-pounds was 25,000. The modulus was 5,800,000, and that's it. The harness test. There were 3 harness tests done, the Brinell, the Vickers, and the Rockwell C. The deliverables for this part are pieces with indentation, the calculated harness, the practical and theoretical, at least 3 indentations to compare, and conclusions. The machines used were the Rockwell, the Vickers, the Brinell, and the optical microscope. Here are some of the results. So the type of test was the Vickers. The material was steel 1045. These are the dimensions. These are the 2 measurements the 2 diagonals, the average. The hardness obtained in average was 292.5. The practical one and the theoretical one was 292.35. So it's almost the same. The formula used for calculating this hardness was this one, found in the presentations. These are the 2 samples. Now, for Rockwell, there were 2 samples as well. These are the 2 practical hardness found, and the average was 24.85. You can see that the hardness can increase depending on its location on the piece. These were 2 of the measurements that we got. The Rinell got these results. The result hardness investigated was 170 to 210. The one we obtained was 192.28 on the first sample and 180 in the second sample. The average was 186.17. This is the formula we used. These are 2 of the samples. They are not really good, really visible, because it was really hard to take the picture in the microscope. Then metallographic analysis. The deliverables are encapsulated piece in bakelite, the photograph of good quality and without scratches, with good fine grains at 100 times, 500 times, and 1,000 times. Also a calculation of grain size at 500 times, as I said on the beginning of the video. The machine used was the machine for metallographic preparations. These are the calculations for the grain size. So I found 22 grains in the 500 times, and the grain size should be 10. This is seen on the 1,000 times, on the 500 times, and on the 100 times. This is the bakelite piece with steel in the middle, and these are the things we use for the practice. For the impact test, the deliverables are the broken samples, the calculation of energy absorbed, and the interpretation of the fracture. The machine was the machine used for impact test, the pendulum. Here's a better representation of it. So here are the 2 samples used. They were both done at 22.4 degrees Celsius, which is at room temperature. Here are the measurements. The energy absorbed on the first one was 31, and the second one was 39 pounds-feet. This is the 39, and this is the 31. They both had ductile fracture, and they had separation after the impact. So why is this practice important? Because as engineers we use materials a lot, and it's important for us to know their properties in order for us to design good mechanisms or machines, because you can't do a failing machine for your work. Finally, here are the references used, the book, and 3 links used for the harness.